Today, the topics will be to look at forced oscillation, and in particular resonance and beats. But before that, I wanted to, as usual, open it up for questions that we can go over whatever you like. And then also, there may be questions on this, so we might get to it then. But if not, and even then again, I thought it would be good to go over a review of what happens when there's repetition between your particular solution candidate and the complementary solution. I see that gave some people some trouble on the online homework yesterday. So I wanted to make sure that was a little more clear. But first, what questions would you like to go over just in general? And I see a question right away. Can we go over question 3.1 on the written homework? Sure, let me bring that up. All right, so 3.1 gives us, let me switch to a new page here. Question 3.1 on written homework 3. It says, we look at this differential equation and this initial value. And what we want to do is find a solution formula. And you can write this as y prime minus or plus negative 2x, y is equal to sine of x. You can use integrating factor since it's first order linear. Once you do that, you'll come up with a mu of e to the, let's see, it's going to be e to the negative 2x, or the integral of negative 2 to the x dx, which is e to the negative x squared plus c, e to the c, e to the negative x squared. So I'm just going through the integrating factor process right now. If you have any questions as I'm doing that, of course, feel free to let me know, but I'm just putting in the work, and we get e to the negative x squared y is going to be e to the x squared, negative x squared, sine of x. And now, at some point, you're going to get this integral plus a c1. And now we can solve for y and get that y is, I won't put that on quite yet, e to the x squared times this integral for this antiderivative. And what the problem asks later then is to approximate this integral to find out what y of 1 should be. Now, you can rewrite this integral in the following way. So this may be the harder part, just to kind of remember another way to write this. You could rewrite this integral, which maybe I'll put in a different color. You can rewrite it like so, where it is the integral from 0 to x of e to the negative, let's say t squared, change the variable to just any other variable but x and y, sine of t dt. It's just a different way to write that antiderivative, and then the rest of this will be the same. And now if you use the initial value information, 1 is equal to y of 0. Let me do a quick check. You'll get 0 for x everywhere, which we go from 0 to 0 on this integral. That means we'll get, nothing here. This will be 0, c1. So I think c1 should be 0, or c1 should be 1. But anyways, the main point is what to do with this integral. In the problem, it asks you to approximate this using Riemann sums, like what you would have seen in Calc 2. Before you actually learn the fundamental theorem of calculus, a lot of times you learn how to do approximations with Riemann sums. So that's what you're asked to do here. Now let me add another page. But if we just focus on finding this, actually, let me do the whole thing. So what you want to find is y of 0. Or not y of 0, y of 1. We know y of 0. You want to find y of 1. If we substitute this directly, that's e to the 1 squared, the integral 0 to 1, e to the negative t squared, sine of t dt, plus e to the 1, e to the 1 squared. Now we know what e is here and here, so that's fine. We can do a computation there. But we don't know what this is exactly. In fact, there is no antiderivative that we can just find right away. So we approximate. Now, in order to do that, we just look at this integral independently. Maybe I'll highlight it here. So we take this integral, and we think in particular about this curve. If we take and we graph that curve over 0 to 1, so here's 0, here's 1, and I take this curve, not sure offhand what it looks like exactly, so let me just bring up a Desmos really quick and graph it. But it's not strictly necessary that we even graph it, but I just want to show you to help illustrate a little better. Negative x squared. And then, okay, so I think from 0 to 1, it looks approximately like this. So what you want to do is you want to approximate this area between the curve and the x-axis using Riemann rectangles. And what the problem says, I mean, whenever you're going to do this, you have to pick how many rectangles you're going to use and so on. And it says divide the interval up into 4 subintervals using left endpoints. So what you do is you divide this interval up into 4, and then you use left endpoints. So that means within each interval, you find the left endpoint of that interval, which would be here, 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 and here, and you use that to create the rectangle. So for example, in this interval, we use this left endpoint that hits the curve at 0, so it has a height of 0. Maybe I'll even use a different color. In this interval, we use this left endpoint, which goes up and hits this height, and so we use this rectangle here. So we'll compute that area. And then in this interval, we use this endpoint, which gives us this here. We get this rectangle, and we compute that area. And then finally, we do the same for this interval. Using this, we compute this area. And we see we'll miss some area here, but we'll gain some area here, and this is not going to be exact, but that's what you're going to want to do. And in order to find these heights, all you're doing is you're substituting in. This is the value 1/4, for instance. You substitute in 1/4 for, in this case, t. So you'd say this height is e to the negative 1/4 squared sine of 1/4. And then computing each of those rectangles, take the sum, and that'll give you an approximation for this integral. And then you can take that approximation, multiply it by e, and add to e. So that's the idea there. Another question someone asked is yesterday's lecture video, some of the steps maybe seem to go a little fast. Okay, yeah, that's fair. That's actually what I want to address in a bit, because like I said, I noticed on yesterday's online homework, people had some trouble. So why don't we just jump then into kind of going over that a bit. It's going to be relevant anyways for the material today, and since people are struggling, I want to try to make it more clear. So when you're picking a particular solution candidate, you want to check whether there's repetition. Let's say we have the following diffie-q. Actually, let's just go over the different types real quick. If you have a differential equation, let's just call it L of x, just so we can generalize it, and say it's not homogeneous. Say that it is e, well, let's say e to something t here. If it's an exponential and there's quote unquote no repetition, so let's organize it like this. So here's your diffie-q. Here will indicate whether there's repetition or not. And I can say more what repetition means if that's not kind of clear from at least what you've seen in the video so far. But if there's no repetition, your xp, and just to clarify, no repetition between x of c and I guess the function f of t, where this is the function f of t here. Oh, someone said it'd be easier to learn if I wrapped all the lecture info. Actually, I want to do that at some point. I want to make videos where it's all wrapping like the whole lesson, but that takes a lot of work. But yeah, that's an amazing comment. So xp, or the particular solution, should be just this itself, e to the alpha t. And actually, a lot of people had put this for that online homework last part. And I tried to indicate it in an announcement, an alternative. But if there's no repetition between the complementary solution and your f of t, that is the part that makes it non-homogeneous here, then you can just essentially put this thing. And that's also true if you have something like, what are the other ones? Another polynomial. So maybe you have, what's the good terminology to use here? Let's say C0 plus C1 t plus dot 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 plus say Cn Tn. I should move this. If again, there's no repetition, then you can just put this thing. A naught plus A1t. Same thing for sine and cosine. But let's say for a second we just have cosine, and it doesn't matter if there's something else in front of it. Let's say you have, I don't know, how about d, some constant. If there's no repetition, you can essentially just put the same thing. Your x of p can be, let's say, a cosine beta t, or ac, plus as for cosine and sine of beta t. Now notice, if you have cosine here, you actually always want to pair cosine and sine with different constants. Now all of this assumed no repetition. So in the case where you have exponential, you have a polynomial, or you have a trig, I mean, it's exactly the same thing if you had sine. So either one would give you the same thing. You would pair both cosine and sine in your particular solution candidate. If there's no repetition, you're more or less just putting what you already have here. So if you have an exponential, your candidate is going to be an exponential. If you have a polynomial, candidate polynomial. If you have trig, you're going to get trig. That's different when you have repetition, but the only difference is taking these and then multiplying them by a polynomial. For example, let's consider, actually, no, let's just consider this example, which we have set up. Suppose you have the following. You have x double prime plus, let's see, 3x prime plus 2x is equal to t e to the, let's see, negative 2t. And we'll even change this value so we get 4. Okay, say we have this. Now, if you find the complementary solution, if it's not immediately clear how you might go about this, but I think we've done a few of these, so I trust you can all do it. But if it's not immediately clear, let me know and we can go back over it. But this should be e to the, let's see, negative t plus c2 e to the negative 2t, just based on how this factors. Its roots will be 1 and negative, or negative 1 and negative 2. This is the complementary solution. Now look at the complementary solution. It's got two terms, and then look at this, what I sometimes call the non-homogeneous part of this equation. The part that if it were 0 would be homogeneous, but because it's not 0, we have it not homogeneous. In particular, what you have is this repetition. Now, it may not seem like repetition at first because what you have in one case is e to the negative 2t, and then in the other case you have t e to the negative 2t. But I claim that this is repetition. So what you would not want to do is just pick this, or this times a, to be your particular candidate. The number of times that e to the negative 2t in some figurative sense is repeated is 3 times. Now, the reason why is, well, we have it one time here, and we have it another time here, but it's with t. Remember before, if we had, let's say, repeated roots, let's say you had x double prime plus, let's say, 2x prime plus 2x, or not 2x, just plus x. If you look at that, you would have a characteristic polynomial of r squared plus 2r plus 1. That has roots of negative 1 twice. If that was the case, what you would do is you would write your complementary solution as being c1 e to the negative t plus c2 e, or c2 t e to the negative t. Having that t there is in some sense an indication of a repetition. You put that t there so you can get something that's linearly independent from this. If we just put c1 e to the negative t plus c2 e to the negative t, we actually only have one term, because you can just add these two together and you could get c1 plus c2 e to the negative t, call that c3 e to the negative t. So this t makes it so that we get linearly independent terms. This term is now linearly independent from this one. So think about that when you're looking at this part, that you can count that as there being a repetition, just like seeing it here means that there was repetition of roots here. That's the way to think about it. So there is e to the negative 2t 2 times here, and then there's, of course, e to the negative 2t once here. That gives you a total of 3 times. Once you have that, once you've counted, and I think I said in a video, quoted it, or said that it was a pseudo number. I can't remember exactly, but it's, it's a count where you do this adjustment here. Then what you do is you take your particular candidate, and what you usually would do if there was no repetition, so you go back to no repetition for a second, you say, okay, well, it would be just e to the negative 2t, and then we multiply it by something. If there was no repetition, that something would just be, let's say, a, capital A. But because there is repetition, what we do in that case is we multiply by a polynomial. And that's all there is to it. You're just scaling it by an appropriate polynomial. Now, the reason we needed to do this count is the polynomial that you multiply by is exactly determined by how many times you have this repetition here. So you have 1, 2, 3 times repetition. That means you're going to have a 3-term polynomial. And I emphasize term because we start with a constant term. So it's not third degree. We don't go up to, cubed. We will actually go up to squared, but there'll be 3 terms because one of the terms is constant. So 3, let's say, pseudo repetitions amounts to a 3-term polynomial. So notice that it's 3 in both cases. Then that will simply be a plus bt plus maybe c t squared. Looks something like this. And again, the reason it's 3 is because you look at the number of times this e to the negative 2t is repeated. We certainly have it once here, and we have it twice here in some sense because we have a t here. That t is, like I mentioned, in the case where we have, let's say, x double prime plus 4x prime plus 4 is equal to 0. The complementary solution in that case would end up being, because there's a double root of -2, so r is equal to -2 twice, then we would say the complementary solution is c1 e to the -2t plus c2 t e to the -2t. Let's look at another example, and it'll be, I guess, kind of a quiz example. I'll set it up and you guys can kind of test your knowledge on whether you're getting it or not. This will be another one. I don't have a nice fancy heading, so I'll just say impromptu example. So I see someone asked a question, so here's a chance to kind of test yourself, see if you're getting it. Say you had, let's even do the same one. We don't need to make it fancy. Let's do, actually, no, let's make it fancy. Not too fancy though. X double prime plus 4x prime plus 4x is equal to t squared e to the, I got to think here, -2t. And I'll tell you that we have, actually, let's do t cubed. If we have the complementary solution is c1 e to the -2t plus c2 c2 times t e to the -2t. And I'll highlight that you have this repetition here. My question to you is, what should our particular candidate be? And you can just put it in chat. It's just going to go to me. So only I'm going to see it. And whether you're right or wrong, it doesn't matter. I'm not going to judge you either way. I just want to see if you guys are getting it. I'll tell you for sure it's going to be x to the -2t. And then the only question, the thing for you to determine is, what will be the polynomial that you multiply by? And you could even say what degree polynomial, or how many terms, however you want to say it. So how many terms should there be? If you want to phrase it that way, that's how we phrased it when I was explaining it just now, or what degree, whatever's easier for you to think of it as. All right, we got a chunk of people chiming in. I see answers such as 3, 4, 5 terms. I'll just present it in terms of terms. Yeah, so I think 3, 4, and 5 are the answers. Let's see what it is. So here, in the first case, if we count repetitions, how many repetitions or pseudo number of times does this appear? We know that this is twice because we have it here and we have it here. So that's something we already know. So the real notion is, what's the pseudo number? Well, if you had t cubed, think about this here. In order to get two terms, or when we had two terms, that would correspond to a highest polynomial degree of 1. So if we have 1, then what we have, like, and when I say 1, I mean degree 1, t to the first power. Then we get two terms. So take the highest degree, add 1 to it. So here we take the highest degree, which is 3, and we add 1 to it. So we take t cubed and then add 1. So the pseudo number is in fact 4. Now we add these up, 4 and 2, and that's the number of terms. So in fact, it's going to be 6. We take a plus b t plus ct squared dt cubed and so on, plus et to the fourth plus ft to the fifth. It's just the same way. I'm going to flip back to the previous problem, where here we had t, and then we counted two terms. First degree counted two terms. Third degree counted 4 terms. Let's do one more impromptu example just to help really reinforce it. Let's do, have we looked at higher degree characteristic polynomials at this point? Have we done things like x triple prime plus 3x double prime? Okay. Yeah, I make videos ahead, so sometimes I lose track of where we're at. Okay, then in that case, let's do again like an x double prime plus 6x prime plus 9x is equal to, let's say, 3t e to the negative 3t plus 7t to the fifth e to the negative 3t plus 2t squared e to the negative 3t. Okay, say we had this. Now I'll just tell you right away, the complementary solution is going to be c1 e to the negative 3t plus c2 t e to the negative 3t. And I'll point out that you've got repetition here. Now my question to you is, when we pick the particular candidate, what should that be? The particular candidate is going to be some polynomial. I'm not sure how long I should leave this, but say like that, times e to the negative 3t. So how many terms do you think we'll have? Like last time, you can answer in chat, see if you can guess it this time. So we've got it here, some repetition, and then there's some repetition here. So what should be the total terms? Okay, I see a couple of people are getting it. I'll wait for a few others to chime in, and whatever you guess is right or wrong, it's okay. I just want to know where you're at. It helps me understand whether I should keep talking about this or we can move on and so on. Okay, I got about half the participants. I'll wait for a few more. Okay, so how many terms? Let's see. Just like last time, we've got repetition of 2. When I say repetition, pseudo number, it's really just all informal terminology for the same thing. So we have repetition of 2 or pseudo number of 2 there. And then in this case, what we do is we look at the highest degree. The highest degree of all the terms that have e to the negative 3t, the highest degree is 5. So we have here, 5 is the highest degree. We only focus on that then. So we take and we say, we have repetition or pseudo number among e to the negative 3t terms, we have 6. Just remember, it's always one higher than the highest degree. We add those together and we get 8. So we multiply a polynomial of a0 plus a sub 1 of times t plus etc. plus a7 t to the 7th power. That would give us 8 terms here. And that, of course, is 2 plus 6. Yeah, so that's all there is to that. Okay, hopefully that makes a little more sense what's happening. In the problem yesterday, the day 14 problem, the part at the end, I can actually, well, I guess everyone had something a little bit different, but just to reiterate from that problem, there was a case where we had something like x double prime plus, I can't remember, I'll just go back to this example. I think it was something like e to the negative t. You had something like this, or maybe there was a 7 here. We had the complementary solution being c1 e to the negative t plus c2 e to the negative 2t. And since there's repetition there between the two, the more general polynomial that you want to multiply by when you do x sub p would have been, if you use a and b, a plus bt e to the negative t. And a lot of people, I think understandably, were just putting a, but you wanted to have this extra plus bt because you had this appearing 2 times, or pseudo number of 2. So you wanted 2 terms here. All right, let's then jump into the material. Oh, actually, someone had a question. When you present the final solution formula, then you will, you'll go through, determine these coefficients by feeding it through the differential equation. Then to get the final one, you'll add everything together. So you would know what A and B are, but whatever they are, this would be the final solution. You have the complementary solution and then the particular solution. This would be your general solution formula, like so. Okay, let's then jump into it. So what is next? Talking about resonance versus beats. So this does have something to do with what we've talked about so far, namely whether there's repetition or not. In one case, we'll have repetition, and in another case, we won't. Namely, in the case of resonance, we'll have repetition, where when I'm talking about repetition here, I mean between the non-homogeneous part and the complementary solution. And in beats, we'll have no repetition. Both these cases to begin with, there is no damping. And in the case of practical resonance, we will have damping. And we're not going to really do computations with practical resonance. I'm just going to mention what it is versus what we talk about to begin with. So as I showed here, we'll have no damping when we talk about resonance and beats to begin with. So it's an undamped system. And the reason we get one versus the other is just whether there's repetition or not between the complementary solution. Let's consider first, how about resonance? So resonance, there's repetition. We're talking about an undamped system. So that would look something like x double prime. There's no cx prime term. That means there's no damping. So it's just something, let's maybe say a times x. Now, if we pick a to be positive, then when we try to find the roots of this characteristic polynomial corresponding to this, when we try to find the complementary solution, what we'll end up getting in that case is going to be c1 cosine of square root of a times x plus c2 sine square root of a times x. You can get that directly just from looking at the characteristic polynomial of this. finding the roots. Your roots are going to be plus and minus square root of a times I. Since there's no real term there, it's just imaginary, we won't have any damping. And that's just what our solution will look like, our complementary solution. The reason I've left this blank over here is, let's say now you have something to the effect of cosine square root of a times x, or sine, either way. And we have whatever number here, maybe lowercase b. Now, the way I've set this up, it's hopefully clear that we do have repetition. If that's the case, then you can imagine what the particular candidate is going to be. Because we have this appearing in some sense twice, then we would say that the xp, the particular candidate, is going to be cosine of square root a times x times, let's say, a naught plus a sub 1. Oops, my apologies. I've been putting x here. I've been meaning to put t. My apologies for the confusion. So the polynomial should be a naught plus a sub 1 times t. Now, we haven't talked at all about the physicality of the system. This is just the pure mathematics based on what we've talked about so far. I'm going to move this up. We talked about how when you have a non-homogeneous linear constant coefficient differential equation, you have to find a particular solution, and how you pick a candidate for that depends on what you have here. Now, our particular candidate is not even quite complete. We also want to add to it, let's say, b naught plus b sub 1 of t times sine of square root at. And cosine and sine always come together. It could be that you end up with only one of them actually being present. It could be that when you feed it through the differential equation, you have a naught and a1 are 0, so you only have sine left. You could have that b naught and b1 are 0, so you only have cosine left. You could have that one of the a's are not 0, one of the b's are not 0, so you could have both cosine and sine, but there's a chance that it could involve both, or it could just be sine. So even though there's a cosine here, we always have to put them together when we pick the particular candidate. And again, the reason I chose a 2-term polynomial is because the pseudo number here is 2. It appears twice, where we just did some computations with pseudo number. So it's the same type of repetition or count. Since there's 2 repetition or 2 pseudo count, we get 2-term polynomials. And notice they're different between sine and cosine. That's important. Now, once we have that, let's think about what's happening here. If we take and we add this all together, let's say we take x is equal to xc plus xp, what's going to happen? You're going to have and actually I'm going to need to give a lot more room here. You're going to have xc, which is c1 cosine root at plus c2 sine root at. Then you're going to have plus a naught cosine root at plus a1t cosine root at. And let's see, can I fit this? Maybe. Then we're going to have b naught sine root at plus b1t sine of root at. Okay, almost fits. Take and add like terms. If you do that, you'll get, I'll call them, we'll get maybe d cosine of root AT. Then you'll get plus e sine of root AT. And when I say d, I'm combining C1 cosine and then A naught. Just to be clear where that's coming from. And the same thing with E. E is just going to be C2 and B naught. Then that leaves us with what? It leaves us with A1t cosine of root AT plus B1t sine of root AT. So what's going to happen now? Well, over time, t is going to grow. So if you think about, now we'll introduce a coordinate axis. If here's t and here's x, it starts out that t is equal to 0. So when t is equal to 0, you actually don't have these terms on the end. You don't have these. What you have is just this. So start out with, you're just some combination of cosine and sine, which amounts to what looks like just a shifted cosine or sine curve. But as t increases, let's say that t is, I don't know, 1,000,000. If t is 1,000,000, now you have 1,000,000 times these amplitudes. Let's say they're, just for the moment, let's say they're just 1. So you have 1,000,000 amplitude times this cosine and sine, which is totally going to dwarf this. So sometimes these latter terms will play a big role, sometimes not. In the beginning they will not, but then later on they will. And I'll graph in a second here what this amounts to. So someone asked, say there's another t in front of the cosine term. Let's say, I'm going to guess we're meaning here. Would there be another repetition? Yes. So if that's a good question, because we just talked about exponentials. But yeah, it's the same idea. If you had a t here, then what would have happened is here, we would have gone up to, let's say, a sub 2 of, times t squared, and then b sub 2 times t squared. So yeah, if you had another t here, it would work exactly the same, where you'd have to increase the number of terms of this polynomial. So that's a good question to ask. Now, what am I talking about here? What I'm saying is, in the beginning, we really just have these two. But then later on, these become more and more dominant, if you will. And what happens is, you start out with some kind of curve, like oscillating sine curve. And then over time, your amplitudes grow. The reason they grow is exactly because of this t here. So this t is what gives you this growing amplitude. Or maybe I can even highlight like this. So that's what causes this growth. And this is resonance. I think I mentioned in some video, I think a review video, about the Tacoma Narrows Bridge, so you'll hear me talk about this again. But if you're aware of that engineering disaster, it was a bridge that started to really move quite a bit thanks to a combination of wind and things like car and foot traffic. And it started essentially oscillating so much that it just tore itself apart. What had happened was there was resonance between the traffic and the wind and various forces acting on the bridge. They sort of acted together to continually amplify the amplitude of the oscillation to the point where, the structure couldn't handle it anymore. So you get this ever increasing amplitude here that gets just bigger and bigger. And it'll go off to infinity. So that's resonance. And that occurs when the non-homogeneous function here what we sometimes call f of t, repeats with one of the terms that occurred in the complementary solution. The two of these act together to increase the amplitude. And mathematically, we see that occurs because we have these terms here where there's a t, and that t is just going to increase, so the amplitudes increase. That's resonance. Now, beats, on the other hand, is where there isn't repetition. And you get some pretty cool looking curves, actually. Say you have, again, an undamped system. You have x double prime plus ax is equal to, now, where a is greater than 0, something like b cosine of, what should I use? Maybe omega t. And it's the case that omega is not equal to square root of a. That is, when you look at the complementary solution, it's going to be the same, c1 cosine square root of a times t plus c2 sine square root of a times t. Now, the particular candidate, there's no repetition. Therefore, or you can think of it alternatively as you only see the cosine omega t one time. You do not see it here. And that's specifically because this omega is not equal to square root of a. So this is not the same as either of the terms in the complementary solution. So I'll color it to kind of indicate that it is not like either of these. Then in that case, you can do, I think, what a lot of you might have expected, which is just to put that thing, cosine omega t, and just multiply it by an undetermined parameter here. And that's it. And since sine and cosine always come in pairs, you also have sine. Now add all this up. You get x of t is equal to x sub p plus, or x sub c plus x sub p. And that will amount to having c1 cosine square root of a t plus c2 sine square root of a t. Then you get plus a cosine omega t plus b sine omega t. Now you can kind of consider these to be in two sets. The set where you have this frequency a, or a period and frequency determined by square root of a. So there's a sort of, let's see, how do I want to write it? The period here is going to be t is equal to 2 pi divided by square root of a, so the frequency is going to be square root of a over 2 pi. Actually, let me move this a little bit. I want to get all three things. I also want to write the natural, or the angular frequency. And I see someone asked a question, which I'll get to in a second, about what happens if a is less than 0. So you have frequency, or you have period frequency and angular frequency. This is what I've forgotten to mention last time, and then I put it in the announcements. Actually, I'm not sure offhand what the exact notation is, so I'll just put theta there for angle. That's going to be root a. And then over here, you have a different period. You have 2 pi over omega. The frequency is omega over 2 pi. And then the angular frequency is just omega. Now these are different. We said that omega is not equal to square root of a. So square root of 8 here, omega different. I'm actually going to bring up a different screen so we can see this in Desmos. We'll just graph some things because I want to show you beats. So I'm going to unshare the iPad. And then I haven't forgotten about the question of a less than 0, and I'll come back to that. But let me bring up Desmos here, and I'll share that with you. So let's do share screen. Can you guys see Desmos here? Okay, cool. Let me bring up something like, doesn't have to be real fancy. Y is equal to cosine of, how about 3? Okay, we'll accept t. And let's give it some more amplitude to make it a little more dramatic. Let's do 4. Okay. Now, this is just cosine of 3t. Notice the frequency, if I decrease it, it takes, like, you go through fewer cycles per second. So as I increase this number, it oscillates faster, meaning you get through more cycles or more radians in a second. Now, let's see what happens. Actually, I'm going to decrease this a little bit. What happens when I, let's say, add something to it? How about 2 cosine of, now, if I just do t, all I'm doing is I'm increasing the amplitude because these are the same frequency. So this is the same thing as like 6 cosine t. But if I change this, let's say like so, now I modify the wavelength or the waveform. If I change it to 3, you can get some really kind of interesting shapes. Now, why it's called beats, let's see. Let me pick another representative one. Yeah, so you can get all sorts of really fun shapes here. I kind of like seeing these. Maybe that was the best one we had. Actually, I want to try one other one. Yeah, okay, that's kind of more what I want. This maybe makes you think more of music. So if we look at this, what you can kind of see is these pockets of waveforms, if you will. I'm going to switch back to the screen, the iPad screen, so I can actually draw, but kind of keep this in mind when I try to draw a waveform similar to this. All right, so we had that example. Now, what I'm talking about when I mention this term of pockets is you have something kind of like this. I'm going to try to recreate it, but I'm not going to do a great job, I don't think. Actually, here, I'll pull it up and draw it while I'm talking to you here. So what it kind of looks like is this. You've got maybe a peak. Yeah, this will do. Okay, so something like this. So when I mention beat envelopes, what I'm talking about is you can kind of see like an envelope that looks sort of like this. So I don't know about you guys, but typically when I think of music and when I think of the term beats in terms of music, this is kind of the mental image that I have. You've got something like, you know, this thing is the beat, if you will. Each of these envelopes. But you saw that you can get all sorts of other interesting behavior, but this is sort of the prototypical image that I think of. Now, the big thing to take away from this is this happens only when you have a difference in the frequencies. I still have it up. This would correspond to, let's say, x of t is equal to 4 cosine of 5t plus 2 cosine of 6t. So that happened when these frequencies were different. If your frequencies are the same, then you'll end up getting the resonance and your amplitudes will just grow. So these kind of have a nice rhythmic timing to it. But in the case of there being repetition, that's where you then get the resonance. So as as again, resonance. That looks something more like this, like so. And that might correspond to something like this. Okay. All right, now I want to check in with you guys. Is this making sense, the difference between these two? Or is it still confusing? What questions do you have about this so far? Oh, actually, and I want to go back to a question someone had. What happens if A is less than 0? If A is less than 0, if we go back here, then what would happen? Say you had x double prime minus, I don't know, minus 4x is equal to whatever. In fact, if you even had, say, b cosine of, how about 3t or something? When you do your characteristic polynomial, what you would get in this case is x of c is c1 e to the 2t plus c2 e to the negative 2t. And then, of course, there's no repetition there, but what you get is something that decays. Actually, that's a good question that brings me to something else I want to mention. Let's say you do have something, maybe not this exactly, but something different. But I will mention that, actually, no, this is a perfect example. So let's kind of run with this question. And I'm going to title this something. I'm going to call this Transient versus Steady State Solutions. So this is a good time to talk about this, I think. Say you had exactly this differential equation, which I'm going to rewrite just a little more cleanly. And you indeed have the complementary solution that is c1 e to the 2t plus c 2 e to the negative 2t, or vice versa, either way. And then your particular solution, because there's no repetition, will be, let's say, a c cosine of 3t plus as sine of 3t. And if you add these up, what you'll get is c1 e to the 2t plus c2 e to the negative 2t plus ac cosine of 3t plus as sine of 3t. Now, whatever these values are, it's going to depend on, one, feeding this back through the differential equation to solve for AC and A sub S, which is going to depend on B. Then C1, C2 are going to depend on initial value information, which we don't have here. But all that aside, just to maybe make it a little more clear what's happening, let's say we end up with a C1, C2 that looks something like e to the 2t minus 7 e to the negative 2t plus 5 cosine 3t. And maybe that's it. Maybe a sub s is 0, but whichever. Now there's a notion of what's a transient versus a steady state solution. Thinking about each one of these, say we've got this one, we'll put in blue. Say we've got this one, which we'll put in orange, and say we have this one, which we'll put in, how about green? If we look at each of them, of course, we add them all up to get the total solution, but individually, we know what they're going to look like. Say here's the x-axis, here's the t-axis. If we look at e to the 2t, that's going to be an exponential, and it's going to look like this. This would be x is e to the 2t. Then we have negative 7 e to the negative 2t. How that's going to look is like this. If it was 7 e to the negative 2t, it would look something like this, but since it's negative, it's going to look something like this. These are going to be negative values. And then finally, what we have is the cosine term, which is going to look something like so. Now, if we think about what happens as t goes to infinity, just looking at each one of these, we have that the blue term goes to infinity. It certainly doesn't go to 0. We have that the green term, 5 cosine 3t, it doesn't go off to infinity or go to 0. It oscillates, but what's important is it does not go to 0. It does not die out, so to speak, or extinguish. However, this term does. The terms that extinguish, that go to 0 or tend towards 0, those are called transient solutions. So this term we would call transient. On the other hand, we would have something like this, which does not die out. This is called the steady state solution. It simply means that it doesn't go to 0. It stays around and it keeps being something that's not going towards 0, or it's not tending towards 0. It's not dying out, so to speak. And same thing here. This is a steady state solution. It doesn't have to go to infinity. It doesn't have to not go infinity. It just has to not go to 0. So if you had a case like this, what would happen is, depends on what your solutions are. In this case, you have e to the 2t, and then you have 5 cosine of 3t. Now, what's going to happen is you're going to have e to the 2t, and then after a while, this negative 7 e to the negative 2t doesn't matter anymore. It's like it's going away. So after a while, it essentially has disappeared. Meanwhile, this is going off to infinity, and this thing is not really changing it too much. So what you might have is something eventually, if you kind of look far enough away, like you look past the origin, ... you look far enough out in terms of t, eventually all that matters is that you have this term, because it's going to be really big, and then you might have like little wiggles in it because of this green term here. But it's going to go off to infinity and everything else is going to kind of disappear. I'm actually going to jump, I'm actually just want to show you this in Desmos, how it'll look. So I'm going to change the screen share, and then I see we've got some questions, so I'll answer those before we go. So let's look back at Desmos, because Desmos is great. And let's look at e to the 2t to show what I'm talking about. And then minus 7 e to the negative 2t. Oh, negative 2t. And then plus 5 cosine of 3t. And yeah, so you see kind of what's happening is in the beginning, you've got this here where there is some oscillation because of the cosine term. But then after a while, after you get past what looks like, what is this, 1? After you get past 1, the cosine term affects this a negligible amount. And what really takes over is the e to the 2t term. And then you have just kind of slight up and downs because of cosine. Like if you were to zoom in really far, you might, like really, really far, you might be able to see some slight variations from the cosine term, but it's going to be vastly dwarfed by the e to the 2t. So to us, we can't really notice any changes. It looks like it's just always increasing upwards, but in fact, there's some slight wiggles because of this. Now I want to check chat real quick. Okay, so what if the roots were different numbers? Oh, like if you had e to the 5t or something like this. If you had, like, it's largely going to be the same as, like, it depends what these roots are. If you had them both positive, let's say, or let's say both negative. Let's say I change this to negative 3t. Now we can see what kind of predictably happens. Oops. Is that the two terms in the beginning will die out, and then what you're left with is just cosine. So the first two terms are transient solutions, they disappear, and the last two term is a steady state solution. If they were both positive, it would depend on what their coefficients were, but you would have basically some kind of war between these two, if this was 2 and this was 3, where you're either going to go off to positive infinity or negative infinity, depending on what the coefficients are here. Since this is a bigger number than this one, and this is negative, it goes off to negative infinity, and so on and so forth. But these would now all be steady state solutions. And if it was an imaginary number, you might have a combination of beats. Let's say you had, I don't know, 2 sine of, oh wow, that's looking crazy, 3t. And if this was, let's say, plus. So here you would have 2 steady state solutions, 2 sine 3t, 5 cosine 3t, but they're again dwarfed by the fact that you have this. Whereas if you get rid of that exponential, you're back to some kind of sine curve. And again, if you modify the numbers here, you get this Beats effect. Okay, that's our time. So thanks for sticking around. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.